In lesson 12.6, we're going to talk about outliers again, but outliers in our correlation and regression situation. So an outlier is an observed data point that is far from the least squares line. That outlier could be also called an influential point. If it's an observation that is influential, if removing it would markedly change the result in the statistical calculation, meaning our slope and our R is going to change, what they say, markedly. It's kind of subjective. You have to decide, does it change it enough to say it's influential, or is it not enough? And this is something you just have to justify. Okay, so you may think it's markedly, somebody else may think it's not so markedly. A lot of times what we'll do is we'll give the results with the influential point and give the results without it, and the person reading the study could actually make the decision. Okay? Our results of statistical calculations are not useful when there are strong influential observations. Okay? When we have those influential observations, they are definitely going to skew our results. Okay? Outliers in either X or Y direction only are usually our influential points. So if I draw my scatter plot, remember we looked at different types of outliers. I have one like that. Notice my Y value falls in with the rest of my Y values. It falls in this range right in here. And my X does as well. But it doesn't go together with what I'm dealing with as far as the other data. Okay? It's my X is too low for the Y that I have there. So only one of them is off from the other calculations. Okay? If I have an outlier that looks like this one, you'll notice that both my X and Y are way too large. Okay, they're much larger than all of the other one. That's probably not going to be an influential point. A general rule of thumb for outliers is that if it's more than 2 standard deviations above or below the least squares regression line, we would consider it an outlier. And then to determine if it's influential, we'll have to go through and look at what happens when we take it out. Okay, the way we find our standard deviation, because this is the standard deviation of the residuals, okay, we use our calculator. You will not have to do this by hand. So if you go into the stat, remember this is the stat, and you go over to tests, okay, you'll see F is linear regression t-test. Now this is the part that we're not actually going to do completely. All we're going to do this for is so that if you look at the next screen, we're going to put L1 and L2. You're going to use the not equal one, okay? And then it's going to give us our standard deviation, where in this case our standard deviation is 16.4. Remember, this is the data that I used from the Exam 3 final exam table. So this was our standard deviation of our residuals that we found from all of those data points. And we're going to use this one and go a little bit further with this type of problem. We're going to use this standard deviation to figure out if we have outliers in this particular data. Remember, that information from the calculator came from the data we've been using all along in this chapter with the third exam score and the final exam score. The easiest way to do that is to use the calculator, and you'll notice that what I have here is our least squares regression line, the negative 173.5 plus 4.83x. Okay? Then what I've done is I've written 2 other equations here. The only part that changed on this one is that I have the plus 2 16.4 and the minus 2 times 16.4. So what I'm doing is I'm taking the least squares regression line for all values of x, and I'm going to add 2 times the standard deviation to get this top line here, and subtract 2 times the standard deviation to get the bottom line. So now you can see here's my least squares regression line, which looks very close to all of those numbers, and this is the cutoff for my upper outliers, and this is the cutoff for my lower outliers. And you can see really the only point that I have concerns about are that one right there. Let me use a different. Okay, that point is going to maybe be an outlier. And which point was that in our table? It was the one that was the 65, 175. Okay, so now I want to decide if that's an influential point. How do I decide if it's influential? I need to remove it and see what happens to my R and see what happens to my slope. Okay, so what I started with is, remember, my least squares regression line was this. Okay, and I had an R of 0.66 for this particular problem. So what happens when I remove this point? So to remove this on your calculator, you just need to highlight the 65 and push delete, and highlight the 175 and press delete. You want to make sure that your 67, 133, and the 71 and 185 stay together. So make sure that you highlight this and press delete, highlight this and press delete. You need to remove both points. Okay, make sure you remove both X and Y so everything else lines up. And then I'm going to do my linear regression again. Okay, so remember, I go to Stat, Calc, and I'm going to push number 8 or number 4, okay, and do my linear regression. And I'm going to come up with a new least squares regression line. This one is negative 355.19 plus 7.39x, and my new R is 0.91. Okay, so now I have to decide, did this markedly change my slope and my Y and my R? Okay, my R went from 0.66 to 0.91. I would say that that's markedly. We have a much stronger correlation in the second situation than we do in the first. If you look at my slope, it went from 0.83 to 7.39. My line is going to be much steeper in this particular problem. My line will look probably something more like this because I have a lower y-intercept, and my line is going to be steeper because of my slope being higher. Okay, so we pretty much covered everything that we're going to talk about as far as correlation and regression. So let's kind of summarize some of the things that we've gone over. First of all, correlation and regression lines only describe linear relationships. Remember, if I do a scatter plot, which is what I should start with, and it doesn't look like it's a linear relationship, you don't want to do anything that we've been doing, the least squares regression line, finding R, finding predictions, and all of that. It doesn't work. We've only dealt with linear relationships here. Okay, that correlation and regression are not resistant to outliers. What that means is the outliers are going to affect our results. Okay, we have other things we've talked about where they're not resistant to outliers. So let's think about some of our measures of center, our mean, median, mode. Out of those three, which ones are not resistant to outliers? Meaning the outliers are going to change our result. Okay, remember we talked about the mean. If you have a really high number or a really low number, that's going to lower or higher our mean. Our mode really is not affected by one value that's going to be really high or really low. And our median is not going to be affected. So the only one that's not resistant to outliers is our mean. Okay, our median and our mode really is not going to be affected by our outliers. Our standard deviation is affected by outliers. Okay, and our interquartile range is what we find with our 5-number summary. We go through and find our first quartile and our third quartile. That's all dealing with medians. So the outlier is not going to affect that. Okay, so the standard deviation and our mean, and now our correlation and regression, are things that are affected by outliers. My medians, my interquartile ranges, my quartiles, they're not going to be affected by those outliers. Okay. Correlation based on averages can be misleading, and we didn't really talk about this, but if I use the average of like 10 different classes, I look at their average on their quiz 3 or exam 3 and their average on their final exam, then it's not going to be as accurate. It's going to be a little misleading because those students that are outliers are averaged in with everybody else. Okay, so it may look like there's a pretty strong correlation when there actually isn't. Okay, beware of extrapolation. We've talked about extrapolation. You saw an example where the value of y that I get when I was using extrapolation was just beyond what it should have been with that 283, I think it was, on the final exam. Okay, and that's making the predictions outside of the range of the X values. Also, you have to be aware of our lurking variables. We've talked about lurking variables quite a bit, and you do need to watch out. There may be a relationship, but that relationship may be based on those lurking variables, not necessarily our independent and our dependent variables. The last thing I want to emphasize is that association or correlation does not imply causation. I've said this a few times, but just because there's a relationship doesn't mean that I actually have one thing causing another. We need to do something further in order to determine that one causes the other. We have three ways we can get a relationship or an association. We have just plain old coincidence. Let's say I do a study on shoe size and number of classes. Okay, and I find I get a really strong R. Okay, my R is 0.7. That's probably a coincidence. Okay, our lurking variables can also cause an association. If I have eating carrots and I'm looking at making free throws, okay, the more carrots you eat, the more free throws you make. There may be maybe I find a relationship between that, but there's a good chance that people who eat carrots are athletic, and they are going to make more free throws than people are not athletic. Okay, it could be those lurking variables that are causing the association. Or I may actually have one variable that causes the other. Healthy eating and weight loss. Okay, and in order to determine that, there must have been some sort of an experiment to see if X actually causes Y, and we controlled those lurking variables, like exercising. You eat healthy and you exercise, well, you're going to lose more weight. Okay, if you're only eating healthy, we want to just look at eating healthy and losing weight, nothing else. So we had to control those other lurking variables. Okay, so that's the way we're going to do these kind of experiments later on in this course.